All right, so this is our second video on the topic of linear differential equations, which we'll be talking about for most of the rest of the the rest of the semester. This week, the first video was on just some general notation and definition of what an operator is. It's just a way that we can convey complicated information without writing out a whole bunch of stuff all the time. All right, so we'll use that some more in this. And just kind of go through the general idea behind linear equations. I'm going to skip over the methods of what we're going to learn later and just kind of illustrate what the process is that we're going to use. And then each step of the process we will talk about individually in later videos. So a linear equation, or a linear differential operator, I should say, is an operator L of y, which just takes some function y, and it represents it as a certain expression defined in this manner. So just a sum of a bunch of different terms. Each term has some coefficient, which doesn't depend on y, but depends on the independent variable possibly. And for most of the applications we're going to see, these coefficients aren't going to actually be functions, but they'll be just numbers. All right. But this is the general form of what we call an nth order linear differential operator, because up to the nth derivative of the function could appear in this expression. But notice the point of the structure here is y and each of its derivatives appear in its own term, and they're all to the first power. And that's really what makes this a linear operator. So again, each of these functions, p0 of x, p1 of x, and so on, are just some expressions in x, but for most problems we're going to deal with, they're just going to be constants. So the general problem we're kind of looking at is solving an equation where we have this expression, L of y, is set equal to some given function, phi of x. And we want to solve that differential equation for y. And this is an nth order linear equation. So as a simple example, this equation we have here is a second order linear equation. So you see we have the form as above. The function y, its first derivative and second derivative are appearing. The coefficients for each of these are respectively e to the x, and then 1. So 1 is the coefficient in front of the second derivative. And in this case, our function phi of x is the sine of x. So this is the general format of a linear differential equation, and in this case, a second order linear differential equation. So applications we'll also talk about a little bit later. Just as we saw applications to first order equations, we talked about falling objects and mixing problems and exponential growth and decay. Other applications involve more complicated models. And in general, the higher the order of the differential equation you're using to model some situation, the more complex the problem is. So we're going to focus on second order problems. One of those examples that we'll talk about are how things can vibrate, or another word you'll see is oscillate. So things that vibrate up and down due to some forces acting on it. We can model the future position of such objects based on initial conditions about the object, where it was when we first saw it, how fast it was going, and in what direction it was moving. And then we can model its position through time by solving a second order differential equation, linear differential equation. Another application that we can see is how the current in an electric circuit can often be modeled by a differential equation. Therefore, solving this differential equation can allow us to predict the amount of electric current within a certain circuit at any given time. And this allows engineers to predict that in some future time, the circuit isn't going to be overloaded with too much electricity and then burn out. So these are simple things that can be done to see how these applications do exist. And there's a lot more applications than what we're going to see. This is just an introductory course. More modern applications are being identified all the time. And for example, many problems in predicting economic trends start falling into quite complicated differential equation models but they are still just differential equation models. So we have the ability to gain information by studying these mathematical models. So the general method is what we're going to talk about. I'll present this in a very general format, and then we'll go through an example. But the steps in the example, we're going to skip over how we determine certain things because those are going to be the things we're going to learn about later. But this is just to illustrate the general method of how we solve such problems. So we're given some nth order linear equation, L of y equals phi of x. Phi of x is a given function, and L of y is that expression that we have on the previous slide involving some sum of terms with different derivatives of y with possible some coefficients in front of them. So the first step is we are going to find a way of determining one particular solution. When I mean particular, I mean this is going to be some function which we're calling y sub p, p for the particular solution. This is going to be a specific function. If you remember from first order equations, we would find a general solution, and this general solution would have some unknown constant appearing. And then we'd have to use some initial condition to determine what that constant is. In this case, we're actually going to find a one specific function, and there won't be any constants involved. But this is just our first step. It gives us some solution to the differential equation, but this solution may not solve or satisfy the given initial conditions that we have. So in many cases, this y sub p won't be our final answer. We'll have to add something to it to make it fit the initial conditions while maintaining that the new function we construct still satisfies this differential equation, L of y equals phi of x. So that's the first step, and we'll talk about that a little later. What we're going to talk about next is the second step. So this week, we'll talk about how to solve the second step. We're going to determine n independent solutions. So we're going to find n different functions. Independent really is a term that you can read about in the book and you'll learn more about in detail in a linear algebra course. But for us, we won't really, this will happen naturally. But the idea of independent functions means they're fundamentally different functions. Right? So they're not just one function can't just be constructed by the others by simple adding and subtracting of terms. So how do we find these n solutions? Well, that's what we're going to talk about next. We're going to look at a simpler problem. We're going to look at the equation which is called the homogeneous equation. And this use of the word homogeneous is not the same as what we talked about previously for first order equations. This is describing a linear equation where the phi of x function is 0. This dramatically simplifies the problem of finding the solutions to this equation. But the solution to this equation is going to be something we'll need to use to solve our general problem. So when we find these n functions that solve this homogeneous equation, we can construct a general solution called y sub h for the homogeneous solution. And the linearity of L is what makes this make sense. Because if I plug y sub h into our differential operator L, it's just like plugging in this sum. And if I plug in this sum, because it's a linear operator, I can think of it as just looking at L applied to each of these terms individually and then adding them up. But they're all equal to 0, so the sum is 0. So this y sub h is going to be the general solution of this equation, the homogeneous equation, and these unknown constants, c1, c2, up through cn, are playing the role of the constant c that we did in the first order equations. We need some initial conditions to determine them. But because the order of our equation is more than 1, we need more than one initial condition in order to solve for all of these constants. Generally speaking, if you have a second order equation, you'll need 2 initial conditions. A third order, you'll need 3. Because the idea is the initial conditions each give you an equation. So if you have 3 equations and 3 unknowns, you should be able to solve for those constants uniquely. So these are the 2 parts of our general solution. And what we do is, once we define these two functions, y sub p and y sub h, we just add them together and define our solution, our general solution y. to our problem. Again, because of the linearity of the operation L that we're using to define our equation, L of y is just going to be L of p, yp, plus L of yh. But L of yp was chosen, so that would be our phi of x. And the y sub h is chosen so that L of that is 0. So we still have a solution. So both y sub p and both y sub p and this y are both solutions to the original problem, except now y has this extra term, y sub h, which has our unknown constants in it, which we can now use to determine those constants by some initial conditions. So let's look at an example. And again, we're not going to go through the details of how we got these solutions. That's what we're going to talk about later. This is just to illustrate how this two-step process works. So in this case, we have a second-order linear equation. The phi of x function is x squared, as we see on the right-hand side. And then we have two initial conditions because we're going to have two constants to determine. So there is, just putting this into the general notation of our problem, L of y is given by this expression, y double prime plus 2y prime plus y, and our phi of x in this case is the function x squared. So notice that if we let y sub p be this quadratic function, it does satisfy our equation. In other words, if you take this as your function, y, and plug it into our equation up here, it will satisfy it. And you should take a moment and just do that and check that it does actually satisfy that. So this is our particular solution. However, if you look at the solution, it doesn't satisfy our initial conditions. It may, by accident, satisfy them, and if it does, then you're done. But generally it won't. So we have to add this second term, this y sub h, that will help us determine the solution that will actually satisfy the initial conditions. So how do we find this? Remember, we consider the easier homogeneous problem, L of y equals 0, and it's a second order, so what we're going to see is there's going to be two simple independent solutions that we'll be able to find. And finding these is actually very easy when you're considering the coefficients being only constants. So in this case, we have 1 times y double prime plus 2 times y prime plus 1 times y. Those are all just numbers. So when they're all just numbers or constants, this is extremely easy to solve and to identify these two solutions, y1 and y2. And if it was a third order equation, we'd be able to find 3. And we'll see that it really has not much to do with calculus, it has to do with algebra. Some algebraic observations will allow us to find these functions. So right now we're just going to pretend that we know how to do that, and we found that these are the two solutions to this homogeneous equation, L of y equals 0. So they let us create a general solution, y sub h, by adding some unknown constant c1 times e to the negative x, plus some unknown constant c2 times x times e to the negative x. So that's our y sub h. And it satisfies, because of linearity of L, the equation L of y equals 0. So we define our general solution to be the sum of the two things we've found, the particular solution and the solution to the homogeneous equation. So that tells us what y is in specific terms. We have our y sub p plus our y sub h. And y sub h is the key because it contains the unknown constants, which we can now determine by going back and plugging them into the initial conditions to figure out what C1 and C2 are. So here's our problem. We found our particular solution, which we'll discuss later how to do that. We found our general solution to the homogeneous problem, which we will discuss next in the next video, how to do that. And we construct, by adding those two together, our general solution y. So how do we make sure that the initial conditions are satisfied? These two steps have guaranteed that y is a solution to the differential equation. We just now have to determine the constants c1 and c2 so that the initial conditions are satisfied. So we need to compute the first derivative because one of our conditions involves the first derivative. So we take the derivative of y. Again, you can just verify this on your own. Just pause the video if you want and just kind of double check that you know how to do this. It's basic calculus stuff. Now we use that and our equation for y, and we plug them into the initial conditions. Again, y of 0 equals 1. What does that mean? It means I take my equation for y, I let x be 0 here, and then what I'm left with is not much. We have a 6 plus c1. So 6 plus c1 has to be equal to y of 0, so that's equal to 1. So that tells us that c1 is negative 5. Now we take the second initial condition. Y prime of 0 equals 0. We go to y prime. Let x equals 0 in this case. Again, a lot of things simplify. And we take that expression, after we plug in 0 for x, we set it equal to 0. We also plug in negative 5 for c1, and we just do a little algebra, and we find that c2 is the constant negative 1. So that's how we determine the constants, and now we know what the exact unique solution is to this problem. We find a particular solution, which will involve one method that we will discuss later. We define the homogeneous solution, which is kind of the adjustment factor that we have to add to y sub p so that we can actually make y match the initial conditions. And in this case, we get our final solution, which is unique.